Hello everyone, my name is Yiming Zhao. Welcome to my video presentation about the linear time algorithm for discrete radius optimally augmenting paths in a metric space. Let me first introduce the path graph and the metric space. A path graph with vertices can be listed from v1 to vn, such that their edges are vi plus 1, where I ranges from 1 to n minus 1. A metric space satisfies an important property, triangle inequality, which the distance between Vi and Vj plus the distance between Vj and Vk is no less than the distance between Vi and Vk. We could define discrete center and radius for a given graph. For example, a discrete center for a path is a vertex Vc. C ranges from 1 to n and minimizes the maximum distance from itself to all other vertices. And the discrete radius is the longest distance from the center Vc to all other vertices. And a continuous center is defined with respect to all vertices of the path, but it may be a point in the interior of an edge. Next, let me show you the problem statement. For a given path graph, we try to add a new edge Vi Vj to connect two vertices Vi and Vj such that the radius of the new graph is minimized. Like this picture shows, we try to find an optimal edge among all the possible new edges. For this problem, there is no previous work in the literature to the best of our knowledge. A straightforward solution is trying all order of n square new edges, which would take at least order of n square time. And we will give a linear times algorithm for this problem. Whereas augmentation problem has been studied before, we try to add a new edge to a given graph such that a specific metric, like the radius or the diameter of the resulting graph, is optimized. We need to know a discrete diameter is defined as the maximum distance between any two vertices of the graph. A continuous diameter is defined with respect to all points of the graph. Given a path graph in the metric space, Jonathan and Wang proposed a linear time algorithm to minimize the continuous radius of the resulting graph in 2019. And Wang proposed an order of n times log n time algorithm to minimize the discrete diameter of the resulting graph in 2017. For a path in the Euclidean plan, the Carufel proposed a linear time algorithm to minimize the continuous diameter of the resulting graph in 2016. For a geometric tree of n vertices in the Euclidean plan, the Carufel proposed an order of n times log n time algorithm to minimize the continuous diameter of the resulting graph in 2017. For a tree of n vertices in a metric space, Below proposed an order of n times log n time algorithm to minimize the discrete diameter of the resulting graph in 2018. And for a general tree of n vertices, Below proposed an order of n squared time algorithm, which is time optimal, to minimize the discrete diameter of the resulting graph in 2018. O and M proposed an order of n squared times log n cubic time algorithm to minimize the continuous diameter of the resulting graph in 2016. We need to know that the radius of a graph may not be equal to its diameter divided by 2. For example, consider that if we connect v1 and vn for a path graph, the resulting graph would be a cycle, and we assume all edges have length of 1, like this picture shows. Then one can verify the diameter of the resulting graph is n over 2, and the radius of the resulting graph is also n over 2. In our approach, we consider all possible configurations of an optimal solution, which is determined by the location of the center Vc, farthest vertex Va, where A is the index, and the shortest path between Vc and Va, which is denoted as pi. We would have a constant number of configurations. For each configuration, we compute a candidate solution in linear time such that if an optimal solution belongs to that configuration, then the candidate solution is also an optimal solution. In the end, among the constant number of candidate solutions, we return the one with the minimum radius as the optimal solution. Next, I will show you how configurations are partitioned. We assume E Vi Vj is an optimal solution. Based on the location of the center, if the center doesn't lie on the subpath between Vi and Vj, then we have case 1. Like this picture shows, center lies on the red passes. Otherwise, the center lies on the subpath between Vi and Vj, like the red passes in this picture. Then we have case 2. For case 1, if the center is a subpath between V1 and V1 and Vi, we have case 1.1. Otherwise, we have case 1.2. For case 2, we consider the location of the farthest vertex Va. If the farthest vertex Va is V1, then we have case 2.1. For case 2.1, we consider whether the newly added edge EVI-Vj belongs to the shortest path between Vc and Va. If so, we have the case 2.1.1 like this picture shows. Otherwise, we have case 2.1.2. Then we go back to case 2. If the farthest vertex Va is Vn, then we have case 2.2. If the farthest vertex Va belongs to the subpath between Vi and Vj, then we have case 2.3. We need to know that the case 1.2 is symmetric to case 1.1. Case 2.2 is symmetric to case 2.1, so we don't need to consider case 1.2 and 2.2. In the next, I will show you the algorithm to compute an optimal solution for each case. First, for the case 1.1, the center lies on the subpath between V1 and Vi. We use Gij to denote the resulting graph after adding EVI to the path P. dg uv is the distance between u and v in the graph G. We have an observation that the farthest vertex is either v1 or some vertices lying on the subpath between vi and vn. Then, the radius is either the distance from v1 to vc or the distance from vc to vi plus the the farthest distance from Vi to all vertices on the subpath between subpath Vi to Vn. Then, based on this observation, we know that for each pair of ij, we have a maximum distance from Vi to all vertices of the subpath between Vi and Vn. For each I, we define Ji could minimize such maximum distance among all j larger than I, and such minimized maximum distance is lambda I. Based on Jonathan and Wang's previous work, Ji is less than or equal to Ji plus 1 based on some monotonicity properties and triangle inequality. So Ji and lambda I can be computed in linear time. Next, we define Ki as the largest index ranges from 1 to I, such that the distance from V1 to Vk is less than or equal to the distance from Vk to Vi plus lambda I. Then we have an observation. For each I ranges from 1 to n minus 1, the corresponding candidate center is either Ki or Ki plus 1. Based on some monotonicity properties, we know the Ki is less than or equal to Ki plus 1. So in our algorithm, we first compute Ji and lambda I in linear time. Then the candidate center for each I is either Ki or Ki plus 1. Because the monotonicity properties of the Ki, all candidate centers and radius can be computed by a linear scan. So we return the solution with the minimum radius as a candidate solution for case 1.1. Next, for case 2.1.1, the center lies on the subpath between Vi and Vj, and the farthest vertex is V1. And the newly added edge EVI-Vj belongs to the shortest path between the center to the farthest vertex. We define Cij as is a cycle constituted by the subpath between Vi and Vj and the newly added edge EVI-Vj. We had an observation that if we connected Vi and Vc, then the length of the cycle CIC is less than or equal to the length of the cycle Cij. This implies the radius of the graph GIC is less than or equal to the radius of the graph GIJ, which means VIVC is also an optimal solution, with VC is the center of the graph GIC. So we don't need to compute an optimal solution for this case, because this case can be reduced to the case 1.2. Similarly, for case 2.1.2, the center lies on the superpath between Vi and Vj. The farthest vertex is V1, and the newly added edge is not belong to the shortest path between Vc to Va. We also could connect Vc and Vj, and then the Vc-Vj is also an optimal solution, with Vc is the center of the graph GCJ. So this case can be reduced to case 1.1. For case 2.3, for case 2.3, we assume C is smaller than A, and in this case, both of the center Vc and the farthest vertex belongs to the superpath between Vc and Vj. If we connected Vc and Vj, then EVC-Vj is also an optimal solution, with Vc is the center of the graph GCJ. So this case can be reduced to case 1.1. In summary, we have a constant number of configurations, and for each configuration, some monotonicity properties and triangle inequality allow us to compute a candidate solution in linear time. So finally, among the constant number of candidate solutions, we retain the one with the minimum radius as the optimal solution. Okay, that's all. Thanks for your attention.